All right. Welcome everybody to my Thesis Defence talk. Nate, should I go ahead?
I'll just say a few remarks. As Shoria just noted, welcome everyone. Today is definitely a very exciting day. First, I want to thank the committee. So this is Marshall, Michael, and Usman, and everyone else that's joining us remotely today. Shoria and I have worked together for, I believe, over 6 years, or almost 6 years, and he's accomplished a tremendous amount during that time. So this should be a very exciting defense. With that said, just a comment on process and procedure. Shoria is going to present his work for about 55 minutes, and then we'll enter into Q&A. We'll start with the committee, and then we'll open it up more broadly, and then come back to the committee. And I am pleased to see that Marshall has just joined us. So that means everybody is present, and I'll turn it over to you, Shoria.
All right. Thank you, Nate. Thanks a lot. Thank you again, committee, for being for my defense talk. And I'm really excited to talk about my thesis dissertation work. So consider urban search and rescue situation like the one that's just shown here. In disaster environments where we don't have a prior map of what the world looks like, it is essential for rescue agents to be able to navigate in these environments efficiently. In order to be able to do that, they need to be able to build a probabilistic representation of the world that enables them to determine which regions are easy to traverse and which regions aren't. And for this, the standard representation that we use in robotics is to use a volumetric map. Now, the state of the art in volumetric mapping for robotic applications is OptiMap. And unfortunately, in the presence of sensor noise, these representations get blurred. And the reason for that could be discussed a little later, but it's important to note that the artifacts that you see in these maps can adversely impact autonomy and intelligent navigation. So for instance, for this region, which was a glancing wall, a robot doesn't necessarily know with high confidence whether that's a region that it could go through or not. So taking a step back to see the bigger picture, this is an instance of a full dense SLAM problem. And the dense SLAM problem essentially is a question of simultaneously localizing and mapping. So the localization part determines the set of camera poses that a robot could have gone through. And the map then is an estimate of the distribution of what the world looks like. And we are only given sensor measurements corresponding to these poses and some estimate of odometry of how the robot might have moved between time instances. So as you can imagine, it's a very complex problem to back out both the distribution of poses and the possible maps given just camera information and odometry. And doing this as a joint inference is typically very hard for dense applications. So in order to make this tractable, we use decomposition, where we decompose this joint prior into a posterior over the space of trajectories and a posterior over the space of maps. So what this looks like in terms of an intuition is that, say, for example, given a geometric object like the one shown over here, for a given robot, we could sample a possible trajectory from the space of trajectories, and given this perspective, the robot can have an estimate of what the map would look like. Consequently, there could be another trajectory estimate that could explain a map differently, given how the robot has moved, and so on and so forth. It is interesting to note that all of these map posteriors are equally likely, given the measurements that the robot has obtained. And so this leads to an interesting observation, and the most important observation, which is that inferring joint map occupancy is exponentially hard. And so say, for example, we discretize the map into a set of cells. And for each cell, we give a label of it being occupied or unoccupied. And essentially, given a sensor measurement, a version of the map that could explain the sensor measurement, for example, would be the instance here where we we highlight the cell that the ray intersected to be occupied. However, the same measurement could also be explained by a map that looks like this, or like that, or even another map such as that. All of these are valid hypotheses of the map to get a sensor measurement as shown in the figure on the bottom. In fact, for each of these particular cells, there are 2 to the power m possible states of the map. And that's why thinking about this posterior is really hard. So conventional representation make 2 simplifying assumptions to make this feasible inference strategy. First, they make an independence of map element assumption. And this allows them to infer the map independently per cell instead of collectively as a joint. And the other thing that conventional map representations do is that they perform incremental updates for efficiency purposes. So a typical map representation, the conventional method that we use, which I showed earlier, is Optimap. And in most of the presentation, we'll be deferring discussion to just comparing with Optimap. But there are a few other representations as well, such as normal distribution maps, which are essentially, one way to think about them is to think of them as occupancy grids, except within each cell, we also store a Gaussian distribution of the sensor endpoints, and Hilbert maps, where the objective is to essentially build a classifier of occupied regions and unoccupied regions, depending on the 3D endpoints within the map. In all these cases, the map elements are still effectively considered to be independent, and the updates are incremental. For instance, in the NDT maps, the update is essentially for every new endpoint that falls into a voxel. The Gaussian distribution is updated by a 1-step update. And for Hilbert maps, essentially every new measurement ends up updating the weighting of the kernels that are used to determine the classifier. So what are the repercussions of making cells independent, and what does it actually look like? So in terms of the occupancy grid here, consider again that a measurement was obtained for a particular ray. So now instead of trying to infer over the space of all possible cells, we treat the update from the ray to individual cells by themselves. So for example, for this particular cell highlighted in orange, since the ray passes, we just use a constant probability, which says reduce the probability of this occupancy map. So if initially the occupancy map was filled with some low prior probability, here designated by a gray value, passing through that voxel would lead it to being empty. Similarly, for a ray that terminates within the cell, we would just bump up the occupancy probability for that cell. And for a cell where no ray information passes through, we make no update. And so after one step of incorporating this ray information into the map, this is what a conventional occupancy grid would do. Now, if say, for example, for a camera with from the same perspective, but a very slightly different ray, we incorporate that information into this map. Note that although the perspective was very similar, because of the same independent cell logic that we used earlier, a cell that was earlier deemed as being occupied gets its probability reduced, and essentially we lose this information about a measurement connecting neighboring cells. And this essentially is where making the independent cell assumption causes the kind of artifacts that we saw earlier in the second slide that I showed. The other issue with doing incremental maps is that essentially it's a form of premature sensor data marginalization. So say, for example, we had a camera pose at t-1, and after time instant of motion, the camera moved to a particular true pose highlighted in the bottom right. Because of sensor drift, or pose estimation drift, to be more precise, the measured depth is set to be at a location further away from the actual true depth. And updating the map with this incorrect measurement because of an incremental update essentially causes the map to start blurring out. So this is a tactic that maps perform, conventional map representations perform in order to make the mapping problem tractable. But any sensor pose uncertainty effectively leads to blurring of the map, which is also suboptimal. So essentially the challenges addressed in Thesis are threefold. The first is we no longer want to make the independent cell assumption. We want to perform joint occupancy inference. What that really means is that we want to explicitly correlate voxels when we get sensor measurements. We want to perform non-incremental mapping so that if there's any sensor pose uncertainty or there's sensor drift between two consecutive poses, we don't prematurely marginalize out that sensor pose information into the map and retain it and marginalize the sensor data only when it is required. And finally, if we only just do these two tasks and the system doesn't work in real time, it's not really useful. So it's also very important and a challenge that this thesis addresses, which is to make all of this real-time viable. So this leads to the thesis statement, which says that ray belief propagation, which is the framework that we discussed, will enable online inference of joint occupancy using forward models and post-posteriors for deliberate robot navigation. In order to see what this means, we're going to list through each of these individual steps through the presentation. So first, we're going to talk about inferring the map posteriors, the joint map posteriors, doing the occupancy inference. So for this section, if you recall the decomposition, we're going to assume that we know what the trajectory estimate is, and our objective is solely the mapping problem, which is given a set of trajectories and sensor measurements, what is the best map estimate? So forward models are a generative model of measurements, and they essentially explain how we get sensor measurements. So probabilistically, it's defined as the probability of getting a measurement given matter existing. And so in this thesis, we restrict our discussion to depth sensors, specifically for RGBD cameras. And for these sort of sensors, which is more precisely mentioned as beam-based depth sensors, the fundamental property that we utilize is that they return the distance to the first measurement generating surface. So in this toy example, again, in this mini occupancy grid, the first measurement generating surface is very likely to lie on the first occupied voxel along the ray, but the generating surface could actually be along any of the three voxels prior to the occupied voxel. In order to capture this intuition, we're going to work through the steps of using a forward model to get the occupancy estimates. So mapping is the inverse problem of using forward models. And so the whole idea, again, like you just mentioned, is what is the generating surface hypothesis that best explains the measurement that we've observed? So the strategy is to first build a forward model, which takes into account the fact that we could get spurious measurements. And once we've got a good estimate of the forward model, we can flip it using Bayes' rule to get the occupancy estimate. So following a standard approach from the early 2010s, we use simple probabilistic map, Bayesian map, a graphical model, where given a camera pose and an occupancy state, we get a depth measurement, Z, where we model the generating surface as a latent variable, small d. And in order to obtain the forward model, which is probability of Z given O, where occupancy here is the equivalent of map, we want to marginalize out the contribution of the latent generating surface. So mathematically, what this looks like is we want to move the generating surface through the entire length of the ray. And so we want to, since we want to marginalize it, we need to first get the estimate of where the generating surface could be. And then given the probability of a measurement generating surface existing at a particular location along the ray, what is the probability of actually seeing the measurement that we've obtained? So say, for example, in this map for the highlighted voxel, if we knew what the voxel occupancy state was, we can come up with a simple model of where the generating surface could lie. This is highlighted in the blue rectangle on the top, where again, it is probability of where the generating surface is given the known voxel occupancy. And there can be two possible occupancy states, as mentioned earlier. So say if a given voxel is occupied, for example, the voxel highlighted in red, as we move along the ray, there's a very high probability that the generating surface lies at the voxel that's occupied. There's a low probability that the generating surface might lie before the occupied voxel. And this could be because of any sort of nuisance measurement, say, for example, somebody walking in front of the voxel, or some dirt or smoke particle that comes in front. But knowing that particular voxel is occupied, it's very unlikely that there would be a measurement that would be obtained from behind a known occupied voxel. Now, for the other state of the voxel being empty, knowing that a particular voxel is empty provides us no effective information of where along that ray a generating surface could lie. Consequently, that probability distribution ends up looking like a uniform prior distribution. So now that we've talked about the two possible variants of that probability distribution along the length of the ray, we come up to the measurement model, so to speak. And all that this tries to describe is what is the probability of seeing the particular measurement value that we've received on the sensor, given that the generating surface for that measurement lies at a particular distance. And for this, we make the standard Gaussian assumption that given a true generating surface location, the sensor measurements are normally distributed around where you'd expect it to be. And so what this forward model looks like then is, again, recall it's the probability of seeing the measurement given knowledge of occupied voxel. And so if the voxel is occupied, the forward model will be an integration of the two probability distributions along the ray, as I've shown earlier. And if it's empty, it will be just a uniform prior multiplied by the same measurement probability. And so now we can use the Bayes rule to flip this. And diagrammatically, what it looks like is, again, just the probability of, and so if we want to determine the probability of a particular cell being occupied, so we essentially plug in chub, and essentially then this is the kind of model that we get. And this is effectively an inverse model, where for cell depth along the ray, we measure the probability of the cell being occupied given this one particular sensor measurement that we received. And as you can note, this probability is low, far away from the measurement. It increases to a peak value at the true measurement value, and then falls off to 0.5 behind it, which makes sense because a measurement does not provide any more information about occluded regions. And this should kind of give an intuition about how a measurement along the ray is being spread between cells close to the measurement. However, this doesn't still solve the problem that we originally set out to do, which was also incorporating the sensor measurement between cells that exist in the map. And so for this, we need to explicitly model inter-cell relationships. And this is where we use the ray belief propagation framework, which was presented earlier in a multi-view geometry context. So in order to see how these ray belief propagation marker random fields work, consider, again, a discretized map volume and a depth camera. And then corresponding to each pixel, we can trace a ray through this volume. For every cell that this ray traverses, we essentially set up an variable node. And so we have corresponding to every single ray. For all the cells that are traversed by the ray, we have an occupancy variable node and a corresponding depth variable node. And these nodes are connected by potential factors. So for each occupancy cell has a prior factor, and each ray together with all the occupancy nodes and the depth variable has a ray depth potential factor. And so multiple rays have their own versions of these ray potential factors. And for rays that go through the same voxel, they share the node within the graph. And this construction within the marker random field essentially couples cells that are touched by multiple rays. And so the joint for this marker random field is expressed as essentially the product over all these potential factors. So just as a quick overview of what these labels, what these occupancy variable nodes look like. So each node can again have a label of 0 for unoccupied and 1 for occupied. And the potential prior factor for each node is essentially just a Bernoulli random variable of occupancy, which essentially states that if the cell is occupied, the incoming message is a constant probability value, gamma. And if it's labeled unoccupied, then it would get a factor value of 1 minus gamma. For the depth variable essentially encodes the event that the ith voxel is occupied and every single voxel before it is empty. So the value of D1R for this depth variable would correspond to the first voxel being empty. The D2 value would correspond to the second voxel being occupied and the first voxel being empty. And the nth value, nth state for this variable would be all the preceding voxels being empty and the nth voxel being occupied. And as you can intuit, this is essentially a proxy for the latent variable that we saw earlier in the simpler forward model for the generating surface location. The Ray depth potential then connects each of these individual events of the latent generating surface existing at a particular location and computes the measurement probability of that latent sensor measurement. And this is actually where we can use learned sensor measurement model. So as a segue, off-the-shelf RGBD cameras, they have characteristic sensor noise. And these are the kind of cameras that you'd expect to see on micro-aerial vehicles. Since they often have smaller baselines because of size, weight, and power constraints, they tend to have increased distortion and depth bias estimates. Specifically for stereo and projective IR-based cameras, this depth bias increases quadratically, along with the standard deviation as well. So in the previous potential factor, we essentially, instead of trying to model individual distortion maps and overall sensor bias, we decide to use per pixel block simple regress fits of bias and variance, with the idea that for every pixel block, if we measure these simplistic measurements, they do a good enough job of encompassing not only overall sensor bias terms, but also incorporate distortion terms in the field of view of a camera. So in order to compute this, I took a checkerboard, a pattern in a motion capture arena, and using sensor poses using the motion capture poses of the checkerboard camera in the entire view frustum, I estimate what the ground truth depth for any particular point on the board is. And I also evaluate the depth image value for that particular pixel from the depth camera. And so after sweeping this board through the entire frustum volume, I can collect a bunch of samples for the ground truth depth distance and the measured depth distance for every single pixel block in the camera. And now given this data, I can easily regress what the bias and the variance is. And the pixel blocks that I use for the results that I'll show, and in this figure, are essentially 20 by 20 pixel blocks. And so the RealSense camera is an 840 by 480 roughly resolution camera, and that's why in the plot on the top left you see 40 rows and roughly about 24 rows and 40 columns. And so, given this information about the potential factors, the objective now for us to put this in a more conventional mapping framework is to find what the occupancy value is for each cell that we use. And in order to get the marginal probability of the occupancy for any particular cell, all we really need to do is sum over the contribution of every single other variable. Now, as you can imagine, naively doing this would be hard, but because of the visibility framework and using loopy belief propagation, specifically sum product belief propagation, it is possible to estimate this marginal occupancy per cell very quickly. And what loopy belief propagation essentially ends up doing is in the first pass all the potential factors sent real valued messages to each of the nodes, which essentially encapsulates what their belief of what the joint distribution between the occupancy nodes and the variables should be. And then all the occupancy nodes collect information from every single ray that comes through them, and then sends it back to all the potential factors in the second step. And this process is repeated a few times until convergence. And so note that although this is an approximate inference of the marginal occupancy and convergence is not guaranteed, in practice, because of the fact that the underlying distributions that we're measuring, because of the fact that we are directly measuring what the depth values are, it ends up being very easy to converge to. So to give you an intuition of how these messages work, consider again an initial map with some low prior probability of occupancy, and consider a first measurement that lies beyond the bounds of the map. So now corresponding to this ray, an outgoing message to each voxel, and over here when I say outgoing message, I'm talking about normalized message of occupancy that goes out to each voxel then is a very low value of probability. Another ray like this one, which terminates in the particular voxel over there, would send out a message that looks a lot like the individual sensor model message that we'd seen earlier. And as a consequence, all the voxels that lie along the ray, depending on the length that the ray traverses through the voxel, get update their probability based on the incoming message and whatever the prior factor had provided them. Now for a ray that has a measurement that's far away from the previously seen voxel, because of the fact that a measurement does not really impact probability values for cells that are further along the ray, it only updates the cells close to the measurement. And for the measurement location that we've seen in the previous ray, it doesn't really impact the probability value for that. And as we get more and more measurements that agree with each other, essentially the evidence of the particular cell being occupied increases. Now consider a contrasting situation over here, where we now get a measurement that conflicts with the first ray's measurement that we've seen. Now in this situation, what ends up happening is that the outgoing message from the first ray reduces its magnitude, and the outgoing message from the new ray also doesn't update the probability of the occupancy of the cell in question as strongly as it would. And so, as expected, the marginal occupancy probability incorporates the forward sensor model uncertainty through the potential factor that we've shown. It couples voxels along a ray and couples information between rays. And to see what this looks like, here's a real-world example of the inference running in real time. And on the top left, you'll be seeing the live depth camera view from the RealSense camera. Note that because it's a stereo IR camera, it's got lots of bias and the variance in the backed-out disparity calculation. On the top right, you'd see the back-projected point cloud and the inferred MRF map. And the bottom left, you'll see the back-projected point cloud and the inferred Optimap for the same set of poses. Note again that the camera poses here are obtained from motion capture. And so we are only doing a mapping process. So as you can see, there's a characteristic waving and stippling patterns in the depth back-projected point cloud. And here we have a human subject. It's actually Aditya, one of the master students in the lab, who's standing, and I'm just moving the camera around him. And at the end, you can notice that the fidelity of the representation, and specifically of the hand and the body, is much higher than that when using Optimap. And to give a much clearer view, this is the output of the inference at different resolutions. So at 1 centimeter, 2 centimeters, and 5 centimeter resolution respectively. And you can note how, given the exact same sensor data and camera poses, MRF maps, by taking into account the learned sensor noise model of the real sense camera, can do a much better job at representing the fidelity of the object in question. So going back to the initial slide that we'd seen, so say for the same living room data set, on the left is the output of Optimap that we'd seen on the second slide of this presentation. With the same data inferred with MRFMap, notice how the glancing wall pixel voxels are no longer marked as empty, and overall the map looks smoother and less noisy. We also performed some results for quantifying the accuracy. And in order to do that, we use a likelihood-based metric that takes into account all traverse voxels along a sensor array, as opposed to treating the map as just a simple binary classifier. And the accuracy results for MRF map essentially remain reasonably high as the map resolution starts getting smaller, whereas it starts suffering significantly for Optimap. So, all right, so we've talked about a framework for being able to couple cells that are next to each other. And after we no longer make the independent cell assumption. So let's take a quick look at how now we can use the same framework, the MRFMap framework, to perform non-incremental mapping. So here, just again, if you look at the decomposition, instead of only looking at the mapping problem as we were doing earlier, now we're going to look at the joint decomposition between the space of trajectories and the map. And just as a quick reminder, this is the view that we had when we started off in the introduction, where we have a posterior over the space of trajectories and a posterior over the space of maps. And the general idea is that given basically any one sample of a trajectory from the posterior estimated over trajectories, we can compute an estimate of the marginal occupancy of the map. Now, trying to do DenseLAM with this decomposition is still really hard. And so in practice, what we can do is that instead of trying to work with all posteriors over the space of trajectories, we can use the maximum likelihood estimate of the trajectories. And so instead of thinking about all possible locations where the robot could have moved, given all the sensor data we have, we get one primary estimate of what the trajectory could be. And now given that maximum likelihood estimate of the trajectory, we try to figure out what the map could look like. And this is basically what we do in typical micro-aerial vehicle autonomy, where we first use a favorite sparse SLAM algorithm to get a maximum likelihood estimate of a trajectory. Excuse me. And then we use that trajectory estimate to build an occupancy grid, which is then used for napping and planning purposes. Now, recall that because of the fact that standard Optimaps marginalize the sensor data out, if there's drift while we are accumulating these maps, then we end up getting blurry map results. And so state-of-the-art submapping approaches have been proposed, which essentially assume that over short time scales, the maps are internally consistent. And so two excellent examples of this are the TSDF plus ESDF combined submaps. Essentially, these are maps which use a volumetric representation just to encode surfaces, and then use that to propagate a Euclidean sign distance field for the purpose of planning. And then, of course, we've got work from Michael's lab, where the map resolution, representation used is Octomaps, but except instead of global Octomap that's updated, there are chunks of maps that are updated with the post-draft backend. And so once we get a loop closure, only the poses that significantly move from the previous estimate need to be moved around, so to speak. So essentially their contribution to the global map is undoed and then undone and then redone with a correct estimate of the camera pose. But unfortunately, it still uses the same independent cell assumptions to make those updates work correctly. The insight here is that MRFMap is a natural submapping framework. And the high-level bit is that we conventionally put maps in metric spaces where we can do planning easily. But inferring in the space of maps is generally hard. But with MRF maps, we don't need to incrementally update the map anymore. We can incorporate any post changes that we have on demand. So we can use the same sort of maximum likelihood trajectory estimates, which is the post graph that these submapping-based approaches use, but use a better map posterior estimator instead of using the map representations that they do. So say, for example, a post graph updates a particular camera pose. We can then seamlessly incorporate it in the next inference step that takes into account all the camera poses. And so in order to show a quick demonstration of this, we artificially add 20% rotation noise and frame-to-frame odometry in the same ICL and UIM dataset. So on the left, you'll be seeing the output of MRFMap and post-graph optimization running in real time. And on the right, just to show what an Optimap would look like without any post-graph optimization. Note, this is not a submapping implementation. What you would see is that as the camera starts rotating towards the edges, on the right, without any post-graph optimization, the walls, because of the rotation error odometry introduced, start getting more and more distorted. Whereas on the left, as the post-graph keeps updating every 400, and so over here, we artificially inject a loop closure every 400 frames. As the map moves around, we can, and I'm going to play this video again. As the camera moves around, it keeps getting updates to where the camera poses could be. And in the next pass of inference, it quickly takes into account any updates to the poses. So right over here is where you can see the camera start rotating and a loop closure comes in right about now, and that updates the inference of the occupancy. It's also a very cool realization that a lot of modern day visual SLAM algorithms use this concept of an active window and an inactive window, where overlapping features are used to determine a subset of sliding window keyframes, so over which constant mini bundle adjustment is performed, whereas there's a slower scale smoothing done on the inactive windows. And up till now, there's not really been any mapping framework that can use that internal active, rapidly updating camera poses to build a map representation. But again, we can use MRF maps and tap in directly into the active window estimate of the keyframes in a visual SLAM framework. So I've talked about how both of these MRF map addresses both of these challenges, but I've not really shown how it's real time and what the metrics are. And so this section tries to show that the choices of the algorithm and the implementation that we've made are essential to make this a real-time possible application. Specifically, I briefly talk about two things of why the choice of using belief propagation is an intelligent decision to make this feasible to do in parallel, and how we address some of the increasing complexity costs of using the MRF map approach. And so recall that for belief propagation, in the first step, all the factors send out messages to every single voxel that they're connected to. Well, this can be done in parallel for every single pixel in a depth image. And all that we really need to store per camera view is just the last outgoing message that each pixel, each ray had to all the voxels that are connected along the ray. And then the next step, where, if you recall, the step was to accumulate all the incoming messages and to update the marginal occupancy. Well, here, each voxel again can be operated on parallel. And this is what essentially is the trick that allows us to make this super complex problem tractable to be performed in real time. And to give you a quick idea of what the timing looks like, for the same sort of resolution, so say for example, for a 1 centimeter map resolution, incorporating just a single, and so here's a plot of the time taken to add every new keyframe into the map. So at 1 centimeter resolution, it takes an order, almost like 2 orders of magnitude longer time for an octomap to incorporate all the depth measurements from a given camera view into the map than MRFMap does. And that's a really significant speed up. Now, the problem though is that unlike octomaps, we do not essentially marginalize the sensor data out. And so we kind of keep the sensor data around for as long as necessary. And so although per keyframe doing the inference is much faster, as the number of keyframes we store increases, the overall time to perform inference increases. And it's not just the time, because we have to iterate through all the cameras, but also the memory storage. And so again, borrowing from some of visual SAM literature, can we do inference only on a sliding window, and somehow once we've got a good estimate of what the camera poses are, marginalize the sensor data pose into a fixed map representation? And so the answer is yes. But the question then remains, like, what is the representation that we should use? And so the choice of representation we make is using Gaussian distributions. And these have been shown to be very descriptive, yet being super succinct. So to give you an idea of what orders we're talking about, typical octomap for the same map environment can take, so for the living room sort of environment, can take up to the order of a megabyte of data to store it. Normal distribution transform occupancy maps take about hundreds of KBs to store the same map at similar levels of fidelity. And hierarchical Gaussian mixture models, as shown by Eckhart and Srivastava, can actually store all of this information in a non-gridded structure in a very, very succinct form. For the purpose of this demonstration, we choose to use the middle implementation, although there's nothing stopping us from using hierarchical Gaussian mixture models. The choice has been made because storing Gaussian distributions within grid still allows us to get an estimate or directly use them within conventional mapping applications. Whereas for storing the map in terms of hierarchical Gaussian mixture models, we'd have to resample from them to fit them into a conventional voxel grid. So in order to do this marginalization process, we use the trick or rather not the trick, we use the property of one of the latent variables that we had in the graph, which was for the camera to be marginalized, we first select all the keyframes that are connected to that particular keyframe to be marginalized. And that choice of connection is made based on the number of common bricks that these cameras are seeing. And for so we perform one pass of inference for this particular set of cameras. And then we look at the distribution of the latent depth generating surface, that variable for each ray. And given this distribution, we find its mode and we render the expected depth per pixel. Now, given this expected depth and the camera pose that we intend to marginalize out, we can back project this expected depth into a point cloud, throw that into the grid structure, and then fit a Gaussian distribution to each grid cell, just like we did for normal distribution transforms. And so what this then allows us to do is to have this framework where at the same time we can be performing from the active keyframes, we can be computing the marginal occupancy. And for the inactive keyframes, as and when we run through a compute or memory budget, we can start marginalizing the map data for those poses. And so what this then looks like is what I like to call the skittle world demonstration, where now as my camera starts moving, I'm going to turn on the map rendering mode. So here I'm showing this running at 1 centimeter resolution. So every single, so what you're seeing right now is essentially a rendering of the marginal occupancy in the active window set. And just now, I set the temporal length of the active window to be 5 keyframes. So just for these 2 keyframes that have just moved out of the active window, we kind of no longer care about the voxels that were touched by by those set of keyframes, but the sensor information remains corresponding to those locations. Interestingly, I don't seem to have controls over this. I'm just going to play this again. And so as the edges between each of those cameras essentially correspond to the number of overlapping voxels that each of these keyframes view. So now as the camera starts moving around, the active volume that I'm performing inference over keeps changing. And eventually I set the marginalizing threshold to be about 10 keyframes. So after we receive the 11th keyframe right over here, you start seeing I'm marginalizing out the expected depth distribution for those particular keyframes. And here is just a rendering mode where I show what the effective normals distribution along those Gaussian voxels is. And here you can see that, depending on the perspective, I render the Gaussian components that are most closely aligned with the camera view. And then as the camera keeps moving around, you still have the view that I showed earlier, where there's an active inference window, and as we keep moving along the list of keyframes, the older keyframes start getting marginalized out into, like I like to call it, the Gaussian skittle world. So this results in significant memory usage advantages. So in the batch mode, where we were not performing this marginalization and we were just essentially in the naive MRF map implementation, we essentially keep increasing the amount of storage that we use. So for example, at the end of about 90 seconds, which is the length of the entire duration of the data set, we end up using almost like 2 gigabytes of GPU memory. However, after marginalizing out the old map regions and only using the active keyframe at any given point of time for performing inference, we strongly limit the memory growth to be roughly proportional to the length of the active number of frames in the active inference window. And in terms of the time per frame, note, if you recall earlier, I'd shown that the time taken for inference kept linearly increasing when we were just using all the keyframes. Well, after using just the active window, the time taken for inference then goes down to roughly about 0.1 seconds in the demonstration that I'd shown before. And note that this is not super accurate timing results because these include the time taken for also visualizing all of those results that I just showed you earlier. But it's still at 10 Hertz, it's still significant enough to be real-time and implemented. Also to note, to get these results, I just used I just used a regular desktop on a reasonably modern GPU, and I have some initial results that show that same inference without any changes can also run on embedded class platforms. However, the performance is much slower. So at the end, hopefully I've convinced you that this thesis effectively addresses all the 3 challenges that we'd set out to tackle. The first was, how to do joint occupancy inference and no longer make the independent cell assumption. Second, to show that using this framework, we can actually deploy it in non-incremental mapping settings. And finally, that doing all of this is practical and feasible to do in real time. Finally, also, that the sensor data can be marginalized in a succinct representation. So just on a parting note, what can we do with another thing that we can do with this MRF map representation, which I have always been very excited about, but unfortunately I don't have time enough to do in the thesis is, can we actually do this full posterior dense slam, right? So if you recall this image that we had earlier, where we were sampling from the space of trajectories and building a map for each of those sample trajectories. Conventionally, in the past, people have tried to do this in 2D setting, and that was using particle filters. And another really cool advantage of using particle filters is that they're also inherently very parallelizable. And what they really do is they approximate the modes of this posterior over trajectories by discrete sample instances. And so as the number of particles increase, you get closer and closer to approximating the true trajectory posterior. And so in order for particle filters to work, essentially you need trick that they use to evaluate this posterior term is that they make an incremental update to the posterior, which consists of having a scan likelihood term and the odometry term. And what this generally looks like is essentially gives a probability of what the next state could be given my current odometry estimate, which can then be refined by a likelihood-based metric, which you would expect to be peaked around the true or very likely location. And what that really means is that, say, if you have a map and you have a sensor measurement from a ground truth, as you move around the ground truth, you would expect to see a peaked likelihood corresponding to the actual ground truth location. And so if you get a likelihood function given your map representation that looks like that, then you can actually effectively deploy a particle filter. And in our past work, we actually did that. So with a Gaussian mixture model representation, we showed that you get these sort of likelihood fields, and then you can do very robust multi-hypothesis trajectory posterior estimation using just this fixed map representation. So a very simple question then is, can we use the succinct map representation that I just showed earlier to do something similar? And so given the same skittle world representation I showed you earlier, I can generate a likelihood image corresponding to the closest Gaussian for every pixel. And then as I displace it around the ground truth, again, you see the sort of negative log likelihood plots that we'd like to see where they peak close to the origin. And the quality of this obviously depends on the resolution that we use for fitting the Gaussian distributions. But even at like a 0.2 meter, so a 2 centimeter voxel resolution, we start seeing plots which suggest that it should be straightforward to use these with particle filters too. And so here's then the broad, grand idea of being able to use MRF maps, right? So for each trajectory sample that we have in the space of a posterior distribution, we can now obtain an on-demand marginal occupancy. So given the sensor images, all we really need to do is just put them at the trajectory estimates along it, compute the marginal occupancy inference, and then estimate the likelihood. And then we can discard that entire setup and then use it for the next trajectory sample. So importantly, instead of earlier where we were forced to store a different copy of the entire occupancy grid for each particle, which made it very intractable to move to 3D, now we don't really need to have an explicit copy of a particle. All we really need is this advantage of on-demand inference of marginal occupancy to estimate what the likelihood of a proposed posterior sample should be, and correspondingly use that to resample the particle filter. And so that essentially brings it all together into the thesis statement, which states that Ray leaf propagation, the framework that we use, enables the online inference of joint occupancy using forward sensor models and also post-posteriors, so that we get models that allow us to do deliberate robot navigation. And that's the end of the talk. Thank you so much for attending. And no man is an island, and there have been so many friends and people who have been along with me on this journey. I couldn't put them all out, but special shout out to the Whiteman crew and they and the RISLab lab members, all of whom I'll definitely keep very strong bonds with. Thank you, and I'm open for questions now. Excellent.
Thank you, Shaurya. I'm sure we would all be clapping if we were there in person. So great job. So now we'll open up to questions with the committee, and we'll go through a round there and then open it up to the broader audience. After that, we'll go through one more round with the committee, and then if there is time, a quick round with the audience again, and then we'll enter into a closed door session for just the committee. So with that said, we'll open up to questions. And Osman, if you would like to get us started as the external member, that would be great. Thank you.
Sure. So I was wondering about the marginalizing into the GMMs, GMM components.
Right.
Is there anything specific about MRF maps that help them kind of play nicely, or can we use the same idea of marginalizing the occupancy grids into GMMs using, say, Octamaps?
So I didn't completely follow the question, but I feel like the question, so correct me if I'm wrong, are you asking about the choice of the representation I'm using for marginalizing? So can I use an occupancy map to marginalize instead of a Gaussian model? Is that the question?
I was wondering if you could replace MRF maps with, say, Octamaps and still do the same marginalized idea using GMM.
All right, gotcha. Well, yes, and that's actually what NDT occupancy maps effectively do. So if you, so what NDT maps do is essentially they use an occupancy grid voxel structure, but instead of just using the logouts to update the probability, they kind of take all the sensor endpoints and then fit a Gaussian distribution to those endpoints. And then what that really allows them to do is that for coarser voxel grid resolution, you get effectively the same amount of information because you're kind of modeling the local geometry within that box. So yes, you could use that, but that is, again, you can only do that in that incremental mapping setting. So the primary benefit of MRFMap is, I like to think of it not as a spatial representation, but as a means of doing inference. And so at the end of the day, you can use whichever representation, the spatial representation you prefer. But the key part is in explicitly taking into account this neighboring information. And it just so happens that for the purpose of inference, it is most convenient for us to do it in the space of voxels. But a very good future direction would be to try and do inference, not in the space of voxels, but use some other sort of underlying map representation to do that.
Another quick question is, so you primarily compared MRF maps with Octamaps.
That's right.
I was wondering if you've also compared you to, say, TSDF fusion. That's also pretty popular representation.
Right. So that's a great question. No, I have not compared it with TSDF, primarily because the objective for deploying MRF maps was to come up with these representations that explicitly encode free space along with occupied space. And so TSDFs effectively, although they do a pretty good job, they don't necessarily explicitly represent free space. They represent voxels that lie around sensor measurement endpoints again. So they don't necessarily reason about complete perspective information.
Okay, thank you.
Great, thank you. Marshall?
Yes, thank you. Great presentation, by the way. Let's see, I have a question on the first part on the joint inference. So maybe I missed something there, but just a quick thing about this. So your graphical model basically encodes the relationship between the rays and the voxel and the consistency between the voxels. But what it doesn't seem to be able to do is to encode the things like, for example, continuity across voxels. Basically, the fact that you're looking at continuous surfaces because there's no interaction between the voxels directly.
Yeah. So that's a great observation, and so to rephrase Marshall's question into like a possible future direction, that would be, for example, so what I've demonstrated here was that voxels are only coupled by sensor ray measurements, and in general we can impose structure on the environment. So if I know what the occupancy of a particular cell is, I could also kind of spread that information spatially to nearby voxels. And that kind of is what approaches such as the Hilbert maps and Gaussian process occupancy maps do. And so that's something that can actually be incorporated within this model. So if required, it can be done to connect adjoining voxels using some sort of like a POTS style model, the old school MRF model. But I feel like that is imposing extra. So depending on application circumstances. So if the engineer who's designing this or deploying this algorithm feels that it is sensible to exploit structural priors, and a possible example of that implementation would be like if your sensor measurements are very sparse. So say, for example, if you have some sort of like a LiDAR point cloud over like long distances where you only get sparse 3D endpoints, and where you want to spread that information, yes, sure. There we can encode this this additional voxel to voxel edges. But for the kind of application that I consider, which is these RGB depth cameras, where all these rays are very tightly compact and packed, I feel it's adding too much. It's adding that spatial information would end up blurring the map more and might not be as useful as one would imagine it to be.
Yeah, so actually, if you were to add that, right, those interactions, doesn't that make your nice computational properties, you know, the parallelism you have on the GPU completely go away, number one?
Yeah, so that will definitely impact the simplification that we do get for these messages. So one of the main reasons that this is tractable, which I've not gone into in this presentation actually, is that because of the structure of this depth potential factor, which is this very neat connection between it's almost like an indicator and a diagonal. What that allows us to do is that when we do the inference across all voxels along the array, instead of doing an exponential summation, we only need to do a linear summation. So just in one pass, we can get the marginal occupancy. And so if we add more edges between voxels themselves, actually, let me take a second to think about it. I think actually it won't be too hard. So if the spatial
Well, we can think about that later.
Yes, sorry, we can talk about this offline.
But one last question about this. I mean, it's just a kind of a suggestion. Your results, of course, qualitatively look great and quantitatively look great, which suggests, of course, that we don't need any of this machinery. And you mentioned that in your earlier answer that you know, the data were very sparse. Of course, you would need things like this. But do you think there is some kind of relationship between the sampling of the measurement, the spatial sampling, the level of noise, right? Those various characteristics of the problem, at which you know, at which point it becomes not necessary to have those continuity things, right? That basically falls out directly from this simpler formulation.
Right. No, absolutely, and that's a very, very astute observation, right? Because so the reason why this becomes more relevant for the kind of sensors I use is because of the small baseline. The uncertainty is really high. Let's say if you had a sensor where you actually, if you did a really, really good job of making your sensor behave the way an ideal beam sensor would, then an appropriately tuned conventional map where you build an inverse sensor model that kind of fits it as well as possible, that might actually do as well as this approach could. But the primary benefit of doing this approach is that, well, now you don't need to really fine tune any inverse model to whatever kind of characteristic you have. You can just use this one generic model where the sensor characteristics are, you just plug what you measure into the inference, and voila, you get occupancy inference without having to fiddle with knobs, really.
Okay, thank you. I'll stop for now.
Thank you. Great questions.
Great, thank you. And Michael.
All right, so yeah, very nice talk and very good, very nice results and extensive work here. Some quick questions. You talk about both factor graphs and Markov random fields. Right. So when do you use which of these and why?
Right. So essentially, so for the Markov random field is essentially just for the inference part. So you could think about the MRF being used only for the map inference. So again, if I show that decomposition, where is it? Right over here. So the Markov random field only goes in the green part where I'm trying to infer the marginal occupancy given the poses. And the factor graph goes in the trajectory estimate, essentially. So and that's basically it. And so that could just be a post-graph optimization where the updates only come through loop closures, but that could also come, the trajectory estimate can also come from like a sparse SLAM algorithm. Say you run, orb SLAM or what have you, and you get a pose estimate. And so the whole idea, or trajectory estimate, and the whole idea is given whatever trajectory estimate, use MRF maps on top to get a posterior over the marginal occupancy.
But so slide 37, I think you were previously on. What you actually showed, the graphical model here, is actually looks like a factor graph.
Yes, right. So it is a factor graph. Yeah.
Okay.
Yeah.
But in terms of optimization, you treat it as a Markov random field then.
That's right.
Okay. And you talked about parallelization on GPU.
Yep.
So how? I guess is GPU suitable for this, since each factor here accesses a different set of occupancies, right? It's not walking through the volume also, it's kind of more random access. Does it still work well, or would you benefit from something else like more machine learning specific hardware or even graph processor?
So I think there are aspects to this which are only feasible to do because of a GPU. So yes, accessing the voxels by themselves, because when you ray trace them, it's not, if you were to just treat each voxel independently, yes, it would be a very inefficient way of doing it. But what I do use, and I've not actually talked about here, is I use this library called GVDB voxels. And it's essentially this, it's a data structure, which it's kind of similar to what voxel hashing did, but in the sense that on the GPU, a set of voxels is stored in a configurable hierarchy, and that's called a brick. And so the lowest element in which you iterate over is a brick. And so that's, in my case, it's an 8 by 8 by 8 set of voxels. And so the data is stored essentially is in like contiguous GPU memory, where there's a mapping between the index space of where that brick could be to where it resides on the GPU. And so when I went, and the library also provides me access to efficient ray tracing, which can do like quick skips through regions which are empty. And so essentially then all I really need to do is I just write these kernels that essentially iterate through each brick and update the corresponding attributes that are stored for each voxel in a brick. And so yes, the way I do at least the forward pass of the messages, which is, for example, which is this step where essentially for every depth image in parallel, I shoot out a ray that touches voxels along it. So that, like you said, is not an optimized GPU operation, because in ideal world, everything would be a gather operation as opposed to each ray going out and just atomically updating the values in the voxels. But in practice, actually, modern day, and specifically because I use CUDA, modern day atomic updates are actually really efficient. And since I operate on like a group of voxels together, the access pattern is like effectively locally cached. So per brick, it's really efficient, and the most of the access cost goes to accessing the brick location, which is more random. I'm sorry, that was a very long-winded way to say that. Yes, there's some disadvantages to doing it in this way on the GPU, but there are also lots of really cool advantages in the way it's been implemented that works.
This is pretty cool, the way it is. Awesome.
And also, sorry, I wanted to mention, I forgot to mention the presentation. MRFMap has been made open source, and so anybody can access it for the research community.
Great. Awesome. Thanks.
Thank you. Thanks for the question.
Great. Thank you to the committee. We'll now open it up to the broader audience. If you would please use the hand waving or raise your hand. I'm not seeing any indications. Shoria, are you seeing anyone?
I only see someone clapping. I see Heather clapping.
Yes. Yeah. A sustained clap.
Wait, sorry. I got a comment from Alex. He says he has a question.
Hi, Shora. Is it okay if I ask my question on voice? I suppose I can raise the hand. Can you hear me?
Yeah, go ahead.
Oh, great. So I had you said you did many improvements to this over Octomap, and I'm just wondering which of the improvements you think has the biggest kind of relative impact on map accuracy. So there are things like you learned a bias variance model of the depth data. You removed the independence of occupancy between cells, and you also chose to not marginalize out sensor data as received, but instead keep it around and perhaps marginalize it out later. So out of those three, do you have one that kind of has the biggest impact, or do you think all three are very important to getting the accurate maps that you got?
Right. That's a great question. To answer your question, oops, I jumped out of it. To specifically for the maps of Aditya that I showed here, because I use ground truth poses over here, the biggest advantage in the quality of in the fidelity came from specifically incorporating the sensor noise model of the RealSense camera. The advantages of doing of the delayed sensor marginalization come into effect more when you don't have ground truth poses and you're actually doing inference over the space of trajectories as well as occupancy. So to distill it here, the biggest advantage is in using the learned noise characteristics.
I see. Okay, and does that include the bias term or just the variance?
It includes the bias term as well, because with the RealSense cameras, I didn't show it. Oops, I didn't show it here, but I can't find the plot really now. But well, for RealSense cameras, yeah, right over here. So you actually get a quadratic bias term with increasing depth. So actually, effectively, when the ground truth is about 4 meters, you get up to 35 centimeters of offset in the measured depth, and that's really significant. And that not taking that into account and into your mapping framework can lead to really, really bad-looking maps. So that's what Octomap does, right? Because it's not taking into account. Some measurements can be really close, some measurements can be really far. And there's just so much noise in it that the poor thing can't really do much about it. It just blurs out the detail.
I see. Okay, great. Thanks.
All right.
By the way.
Thank you. I see Akash raising.
Hi. Yeah, can I ask my question now?
Yeah,
yes, please do.
Yeah. So basically, I wanted to do a little bit of comparison with TSDF. So I didn't understand exactly what the Ray Depth Potential factor did. So is it right for me to say that in a continuous sense, it kind of encodes the SDF function?
So I can answer that with a, so the short version is yes, you can basically get the same properties that you get with an SDF. Right. But you can do it in a better way because you're actually now taking into account the probability of occupancy along the ray. So one of the advantages of having TSDFs, right, is you in the voxels you store what the endpoints are, and then you just store what the distance to the implicit surface representation is. Well, if you actually have Gaussian, if you have this probabilistic set of outgoing messages, what you effectively get is you get the, well, sorry, actually this is not the right plot, but what you get is a depth distribution along any given ray.
Right.
And that allows you to not only reason in terms of just one surface, effectively allows you to reason in space of all the probabilistic generating surfaces for a given perspective.
So in some sense, you're saying basically like you're not integrating your measurements for a certain duration of time and then you do it simultaneously. And one more thing is that you don't really truncate the distance function, right?
Sorry, could you repeat the second part?
So in some sense, like one thing is that it would be similar if you don't truncate the distance function.
Oh, if you don't truncate those, well, I would like to argue that it's a little better than that, because there's not, you can actually model multiple modes along the ray when you're doing inference in this way.
And that's because like you're not integrating I mean, in some sense, like if you kind of do a comparison, you're not integrating the SDF measurements like incrementally, right?
Yeah, it's basically because you're not storing the endpoints and you're actually doing it.
And one more question I had on slide 71, you make a comparison with Octomaps, right? So I guess like the Octomap comparison is actually like the Octomap would be on CPU, right?
Yes, so of course it's on CPU. And so yes, it's not an Octomap implementation on GPU. So sorry, thanks for correcting that. This is not an Octomap. This is just the off-the-shelf Octomap.
Would you say that like Octomap on GPU, I mean, if you use the same kind of voxel hash implementations, like would it be like comparable? Like, I mean,
that would be way faster, right?
I see. Okay.
Because I mean, it's like at that point, you literally all you're doing is just a glorified version of storing endpoints and updating a voxel value. So that'll be really fast.
Right. Okay. Thanks.
Thanks for the question.
Okay, great. At this point, I would ask the committee, so Marshall, Michael, Osman, do you have any further questions?
I have one small question on the on the Gaussian representation at the end, the GMM type thing. At least on the animations that you showed, and maybe I missed something as to how that's computed, but on the animations that you showed, the Gaussian approximation is really, really good. It's very regular, all oriented the right way and all that. How does that happen? I mean, I would not expect that normally from a GMM type thing. I would expect more randomness.
So the first part is that I'm actually using the expected depth image. So that's in a sense it's already the best inferred location of the generating surface given all these locations. And the second part essentially is I just because the brick sizes are so small, right? So for example, for that image that I showed, where is this guy? So like for example, for these images, right? So if you notice, I'm actually showing just the 3 sigma bounds over here. So at the larger bit resolution, because now if the spread of your expected depth points is exactly the way you would expect it to be, then just fitting a Gaussian in a smaller brick space ends up doing a surprisingly good job. So the important thing is normally when you just use a Gaussian, the conventional way of fitting a GMM is to use expectation maximization. And this is an insight that I actually got from Aditya, who worked a lot on using Gaussian mixture models, is that if you just throw the sensor data all together to the expectation maximization process, what happens is that because it doesn't necessarily find a global optimum, it gets very heavily biased to regions where the point density is higher. And so if you don't have a uniform spread of 3D points that you're fitting your Gaussian models to, your fit Gaussian mixtures end up like clumping in the regions where you've got more 3D depth points. And for depth cameras, that ends up being like points that are closer to you. And so all the effort ends up in like trying to fit close by Gaussians really well, and does a terrible job of trying to fit Gaussians that are far away because they're sparser. So one way of actually doing a good job of fitting Gaussians is to impose this discretized voxelization, where you say that, oh, I'm only going to fit a Gaussian to 3D points that lie within this voxelization. And that actually leads to So if you do EM with that, it does a better job. And I think Eckhart also mentioned a little bit of that in his work. In my case, I'm just literally just doing incremental sufficient statistics update. So given all these 3D points that lie in the cell, I literally just do a sufficient statistics. I compute the mean and the standard deviation. And there was some stuff that I've done in terms of writing these OpenGL shaders, so in terms to answer that question of why it looks so good in terms of what the normal maps were. Essentially, what I'm doing over there is for any Gaussian covariance, you can model it as an ellipsoid, and that ellipsoid has a characteristic sphere, and so you can basically map any point on this characteristic sphere to a point on the ellipsoid. And so all I'm doing over there is I'm literally just coloring the ellipsoid by what the corresponding normal on the characteristic sphere would be. And so the way I figure out what is the component that faces the camera is I look at, because most of these components are generally flatter, it's going to be this, the axis, the eigenvector, which corresponds to the smallest eigenvalue of the SVD of the covariance matrix that points to your z direction of the Gaussian. And so that's why essentially z direction is your 0, 0, 1. And so I color it literally by the RGB values for each Gaussian as you move along the surface of the ellipsoid. And that's why for all these Gaussians over here, you see that, they kind of like look like the normals are all on top. But for like, for example, the Gaussians along, the side, I think I can just play it in here. For the Gaussians along the side, you can see that they're actually facing the other way from me, because the normals can be, because the eigenvector can flip. So that's why they're looking in the opposite direction. But some very cool things you can do though is that you can actually make out individual leaves in the data set, which are fit by these small Gaussians. And yeah.
Thank you. Yeah, your enthusiasm answering that question reveals how much time you spent. Okay. That's it.
All right. All right. Very good. Marshall, Osman, any final questions? Or not Marshall, apologies. Michael, Osman, any final questions?
I'm good.
Thank you. Osman?
Me too.
Okay, very good. Shaurya, are you able to create a breakout room for us to discuss?
Yeah, first I'm going to stop recording, I guess.